Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. Imagine taking the mass of our sun, not the volume, just the mass, and compressing it into a sphere roughly the size of the city you live in. Now spin that sphere hundreds of times per second. Now give it a magnetic field a trillion times stronger than Earth's. Now set it beaming 2 jets of electromagnetic radiation into space, like a cosmic lighthouse, sweeping past Earth with the regularity of an atomic clock. That object is real. It exists throughout our galaxy in the hundreds of millions. And it is called a neutron star. Neutron stars are among the most extreme objects in the known universe that still have a physical surface, a distinction that separates them from black holes, which have no surface at all. Today, we're walking through what neutron stars actually are, how they form, what their surface is like, and why the spinning variety, pulsars, were so precise when first discovered that astronomers genuinely considered whether they might be signals from an alien civilization. And in our next episode, we're getting into the collisions that produce gold, platinum, and every heavy element in the universe, and the conspiracy theories about what neutron stars might really be. Stick around for that one. Neutron stars form at the end of the lives of massive stars, those with roughly 8 to 20 times the mass of our Sun. Throughout their lives, these stars burn nuclear fuel in their cores, with the energy released by fusion providing outward pressure that counteracts the inward pull of gravity. This balance is what keeps a star stable throughout its main sequence lifetime. When the fuel finally runs out, the balance tips catastrophically toward gravity. The core, no longer supported by fusion energy, collapses in a fraction of a second, a timescale so fast that the outer layers of the star haven't had time to react. The core compresses with such violence that protons and electrons are forced together to form neutrons, the process that gives neutron stars their name, and the collapse is halted only by neutron degeneracy pressure, a quantum mechanical force that prevents neutrons from being compressed into the same space. The sudden halt of the collapse generates a shock wave that blasts the outer layers of the star outward in one of the most energetic explosions in the universe, a core collapse supernova. What remains after the explosion is the neutron star, the crushed core of the original massive star, now compressed to roughly 12 to 15 miles in diameter, while retaining roughly 1.4 times the mass of our Sun. The conservation of angular momentum during this collapse is what gives neutron stars their extraordinary rotation rates, just as a figure skater spins faster when pulling their arms inward. A star that was rotating slowly over its lifetime spins up to extraordinary speeds as it collapses from a radius of millions of miles to a radius of miles. The result can be a neutron star rotating hundreds of times per second from the moment of its birth. Like, subscribe, and hype the video, because what the surface and interior of this object are like is unlike anything else in the universe. The interior of a neutron star is one of the most exotic environments in the known universe, and some of its properties are still genuinely uncertain even to the physicists who study them. The outermost layer, the crust, is a crystalline lattice of atomic nuclei and electrons, extraordinarily rigid, estimated to be about 10 billion times stronger than steel. This is the only part of a neutron star that behaves like anything resembling a conventional solid surface, and even this layer would be utterly alien by any human standard. Below the crust, the matter transitions into regions of increasingly neutron-rich nuclei, and then into a layer of pure neutrons believed to be in a superfluid state, a quantum mechanical phase of matter with zero viscosity, meaning it flows without any friction whatsoever. A superfluid neutron layer inside a neutron star means the interior can flow and rotate independently of the crust above it, a property that has real, observable consequences for how neutron stars behave, including sudden changes in rotation rate called glitches that we'll get to shortly. At the very core, where densities reach values that no laboratory on Earth can replicate, physicists genuinely don't know what state matter is in. Theoretical proposals range from a condensate of hyperons to a deconfined quark-gluon plasma to more exotic forms of matter that go beyond even our current standard model of particle physics. The core of a neutron star may be the only place in the current universe where matter exists in a form we haven't yet described. In 1967, graduate student Jocelyn Bell at Cambridge University was analyzing data from a radio telescope and noticed something unusual. A repeating radio pulse arriving with extraordinary regularity, once every 1.3373 seconds, with a precision that matched or exceeded the most accurate clocks available at the time. The regularity of the signal was so precise that the Cambridge team seriously considered whether it might be artificial in origin. They temporarily designated the signal LGM1, Little Green Men 1, while working to determine whether a natural explanation existed. The precision of the pulses, combined with their apparent origin from a fixed point in the sky, made an artificial transmitter from another civilization a genuine hypothesis rather than a joke. The eventual natural explanation was both more mundane and more extraordinary than alien transmitters. The pulses were coming from a rapidly rotating neutron star, its magnetic poles oriented such that beams of electromagnetic radiation swept past Earth with each rotation, like the beam of a lighthouse. The extraordinary precision of the pulses was simply a consequence of the extraordinary rotational stability of a massive, dense, compact object. A neutron star's rotation rate changes so slowly that it can serve as a more accurate clock than most human-built timepieces. Jocelyn Bell's discovery earned her supervisor Anthony Hewish a share of the 1974 Nobel Prize in Physics, in a decision that remains controversial because Bell herself, who made the actual discovery, was not included. Like, subscribe and hype the video, and let's get into just how extreme these clocks actually are. The most rapidly rotating neutron stars, called millisecond pulsars, rotate hundreds of times per second and maintain their rotation rates with a long-term stability that rivals or exceeds the best atomic clocks humanity has ever built. The fastest known millisecond pulsar, designated PSR, J1748-2446 AD, rotates 716 times per second, making its surface at the equator move at roughly 24% of the speed of light. The precision of its pulses is so extraordinary that scientists have been able to use it, along with networks of other millisecond pulsars spread across the sky, as a galactic scale detector for gravitational waves, the ripples in spacetime produced by merging black holes and neutron stars billions of light-years away. This technique, called pulsar timing arrays, works by monitoring the precise arrival times of pulses from dozens of millisecond pulsars simultaneously, and looking for correlated timing variations that could only be caused by a gravitational wave passing through the region of space between Earth and those pulsars. In 2023, multiple independent pulsar timing array collaborations announced the first strong evidence for a gravitational wave background, a low-frequency hum of gravitational waves permeating the galaxy, likely produced by the mergers of supermassive black holes throughout the universe's history. The detection was made possible by the extraordinary precision of millisecond pulsars functioning as cosmic clocks distributed across thousands of light-years of space. Even the universe's most precise natural clocks occasionally skip. Pulsars, particularly young pulsars still spinning down from their birth rotation rates, occasionally undergo sudden increases in rotation rate called glitches, where the pulsar abruptly spins slightly faster than it was before, then gradually returns toward its previous spin-down rate over days to weeks. These glitches are believed to be caused by the superfluid interior of the neutron star. As the outer crust gradually slows down through electromagnetic braking, losing rotational energy to the pulsar's radiation, the superfluid interior, flowing without friction, may continue rotating at a slightly higher rate for a period. When the coupling between the superfluid interior and the rigid crust suddenly transfers angular momentum from the faster spinning interior to the crust speeds up abruptly, producing the observed glitch. This explanation is the leading model but hasn't been definitively confirmed, and the details of exactly how the interior and crust interact during a glitch event are still being worked out. In this way, Pulsar timing data, the most precise astronomical measurements routinely made, is simultaneously being used to detect gravitational waves across the galaxy and to probe the exotic interior physics of objects whose cores may contain forms of matter that don't yet appear in any physics textbook. So that's a neutron star, the crushed core of a dead star, 12 miles across, spinning hundreds of times per second, with a magnetic field a trillion times stronger than Earth's, a superfluid interior whose physics we're still working out, and a crust harder than anything else in the universe. And when they pulse, they do it with a precision that's allowing us to detect gravitational waves echoing across the entire galaxy. But here's what we haven't covered yet, and it might be the most extraordinary thing about neutron stars of all. When two of them spiral together and collide, the explosion that results is one of the only known events in the universe capable of producing gold, platinum, and every heavy element heavier than iron. The gold in your jewelry didn't come from a star. It came from two neutron stars colliding billions of years ago. In our next episode, we're getting into that collision, the extraordinary 2017 observation that confirmed it, and the theories, including some genuinely strange ones, about what neutron stars might actually represent in the larger structure of the universe. Stick around for that one. Like, subscribe, and hype the video so you don't miss part 2, and let me know in the comments what you find most extraordinary about neutron stars. I'll see you in the next one.